Edge AI moves machine learning onto devices that sit close to where data is created, so latency, privacy, and offline reliability start to matter as much as model accuracy. The goal here is to understand how to design applications that run well at the edge, not just in the cloud. Exploration is the point where an edge AI idea earns the right to move forward. The goal here is to figure out whether the problem, the constraints, and the data make a real solution possible. A tidy workflow diagram can be useful for planning, but real development keeps circling back. Each pass should sharpen the problem, test assumptions, and expose constraints before more time gets committed. That first gate is about deciding whether the idea deserves effort at all. It reduces uncertainty enough to support a responsible go or no-go decision instead of pretending success is already guaranteed. The purpose here is to separate a promising idea from a project that can actually be justified. The questions in this phase decide whether the team should invest further or reshape the problem first. Those stages have different jobs. Exploration checks viability. Goal setting makes the target measurable. Bootstrapping builds the first version. Iteration improves it. Deployment puts it to use. And support keeps it working in the field. A project can look fine on paper and still fail because the scope is wrong, the hardware budget is too tight, or the needed data never becomes available. Exploration is where those expensive mistakes are still cheap to catch. These are the questions that stop a team from building the wrong thing for the wrong reasons. They cover need, method, feasibility, and the people affected by the system. A good exploration phase forces the core uncertainty into the open. Once those questions are visible, the team can judge the project against reality instead of against enthusiasm. First, decide whether edge AI is needed at all. Then check whether machine learning is even the right tool, whether the system can fit the real latency and resource limits, and who must be satisfied with the outcome. A model can score well and still produce a poor system if it disrupts work, hides important decisions, or creates a bad user experience. The technical result matters, but it is only one part of whether the system should exist. Ethical risk has to be part of the early framing because false alarms, misdetections, and uneven performance change both the data you need and the evaluation you run. Those concerns can decide whether the project should continue. Data work is not a cleanup step after the design is settled. The shape, availability, and quality of the data often decide whether the project is viable before any model is built. If the relevant data cannot be reached early, or if what you can get looks nothing like the real environment, the project may fail before it properly begins. That is why access has to be checked during exploration. Edge data often carries timing, noise, and physical structure that basic summaries miss. The analysis has to examine drift, alignment, gaps, class balance, and the measurement conditions that will shape model behavior later. A production inspection system only makes sense if the team understands what defects exist, how the camera sees them, and whether the samples are representative. The same reasoning applies to a low-power field device. The sensors must produce usable signals under rain, seasonal change, and battery limits before any classifier can be trusted. When the data is missing, the answer is not to guess and move on. The practical move is to arrange access, negotiate collection, or run a small pilot, so the project is shaped by real examples instead of wishful ones. Early exploration gets better when domain specialists join the conversation. People with signal processing, physics, or biology knowledge can spot structure in the measurements that a general model builder might overlook. A DSP engineer may recognize filtering artifacts. A physicist may know what a signal should look like, and a biologist may know which variation is normal. Those judgments affect whether the data can even be interpreted correctly. That mix of skills is valuable because edge AI is not just about training models. It depends on people who can connect physical measurements, system constraints, and deployment behavior into one coherent design. The first gate should produce a clear yes or no, not vague optimism. If the problem, the data, or the operating environment looks wrong, the responsible move is to stop or reshape the idea before the team commits deeper effort. If the problem is vague, the stakeholders are unclear, the environment is hostile, or the data cannot be reached in time, the project should change direction or end. If the answers are good enough, the phase has done its job by lowering the risk of a focus build. The aim is not certainty. The aim is enough clarity to keep the team from spending weeks or months on a project that was never the right one to build. Exploration starts with evidence. The goal here is to judge whether the data, the setting, and the use case are strong enough to justify an edge AI project before any modeling decisions lock you in. A project stays flexible when the first step is to inspect what the data actually shows. That keeps the team from committing to a model or deployment plan before the problem is understood. The first pass should answer a simple question: what evidence is already available, and what evidence can realistically be gathered in the field? In Edge AI, that evidence is often visual, so plots, snapshots, spectrograms, and side-by-side examples become the fastest way to see whether the idea is even plausible. A few minutes of careful inspection can expose noise, missing segments, sensor failure, drift, clipping, or labels that do not really separate the classes. That quick review can also reveal when a signal only looks healthy in aggregate, while the rare events you care about are nearly invisible. Pattern recognition matters because it turns a vague idea into a known kind of system. Once the project resembles a familiar application, the constraints and failure modes become much easier to anticipate. A project starts to make sense when it can be compared with known cases like occupancy detection, anomaly spotting, field sensing, or visual quality inspection. That comparison immediately raises practical questions about connectivity, environmental noise, rare events, and whether inference has to run on the device itself. Different settings behave differently, and that matters from the start. A river monitoring system, a wearable sensor, and a factory camera each demand a different mental model for data collection, deployment, and failure. Riverwatch node gives a small, concrete example of the same reasoning. The point is to inspect the evidence first and ask whether the local patterns are strong enough to support a useful classifier. For a stream monitoring system, the first questions are about separability and consistency. If normal flow, rainfall, turbidity, or contamination events do not leave recognizable traces in the sensor data and images, then model selection is the wrong place to start. When the structure is visible, the team has a reasonable basis for first build. When the evidence is noisy or one-sided, exploration has still been useful because it shows that the sensing plan or the project scope needs to change before modeling can help. The biggest risk is often not the algorithm at all. It is whether the right data exists in the right form, under the right operating conditions, with labels and timing that match the real problem. If representative examples are missing, if the sensor placement is poor, or if the event of interest never appears inside the recording window, the project may be far riskier than it first looked. Exploration makes that visible early, before those assumptions get baked into the architecture. Early data access is valuable because it lets you revise the physical setup, not just the model idea. You can still change sensor count, sampling rate, mounting position, or even the project scope while the cost of change is low. Exploration becomes much stronger when people who know the domain join the review. They can spot structure and failure modes that are easy to miss from the outside. A DSP engineer may notice aliasing or filtering artifacts. A biologist may recognize real variation from a meaningful event, and a manufacturing engineer may understand machine states that never show up clearly in a spreadsheet. Those observations can decide whether the evidence is interpretable at all. That cross-disciplinary ability matters in practice because employers need people who can inspect plots, read images, and connect the signals to what is happening in the field. The useful skill is not only training models, it is judging whether the raw evidence is trustworthy enough to support deployment. Good exploration also asks about responsibility. A technically attractive system can still be a poor idea if it creates unsafe workflows, shifts costs onto the wrong people, or depends on data that cannot be collected ethically. That broader review matters because technical success does not guarantee a responsible outcome. Early inspection is the moment to surface ethical and operational problems, while changing direction is still cheap. The people who live with the system usually know which signals matter. which failures are unacceptable, and which situations appear only in the real world. Bringing them into exploration keeps the project from optimizing the wrong target. The main habit to keep is simple. Use evidence, examples, and domain knowledge to cut uncertainty early. If the signal, the sensors, and the operating context all look reasonable, the project has earned a next step. Riverwatch node shows the logic clearly. When a signal is separable, the setup is plausible, and the experts agree the patterns mean something, the work can move forward. When those pieces are weak, exploration has already saved time by preventing a bad build. That makes visual review and early application matching far more than background work. They're the cheapest way to decide whether an idea deserves more investment. Goal setting in Edge AI starts with defining what success really means, not just chasing a model score. That matters because a system can look good on paper and still fail where it actually has to operate. Accuracy is only one part of the picture. In edge systems, latency, power, workflow fit, safety, and maintenance all shape whether the project actually works in the field. The important idea now is scope. Goals belong to the whole project, not just the model. A good system has to perform technically, fit the workflow, avoid harm, and stay supportable after deployment. Technical goals cover model behavior. Systemic goals cover how the device fits into real operations. Ethical goals cover impact on people, and support goals cover what happens after launch. Putting all four together gives a realistic definition of success. That broader view is not extra paperwork. It is what keeps a team from optimizing a model that solves the wrong problem. Measurable goals turn a wish into a standard that everyone can judge before pressure and hindsight distort the decision. In Edge AI, those standards need to be written early and checked again after deployment, because field conditions often reveal problems the training metrics never showed. A concrete example makes the idea easier to use. Riverwatch Node is a field monitoring system, and its success depends on turning a vague idea into specific decision points. At first, the project sounds simple. Detect meaningful events locally and forward only the important ones. Once the team defines success, though, the real constraints start to appear. Each goal type asks a different question. The technical question is whether the detector works under changing conditions. The systemic question is whether it helps the field response and fits the power budget. The ethical question is whether it overreaches, and the support question is whether it can be maintained as the environment changes. That is why goal setting happens at the project level. The team has to define success in technical, systemic, ethical, and operational terms together, or the final system will be judged by the wrong standard. Minimum viable performance gives the team a stopping point before enthusiasm takes over. The idea is to set the lowest acceptable level for each goal type while the project is still cheap to change. Once people have invested time, money, and reputation, it becomes hard to quit cleanly. Clear thresholds make the decision simpler. If the system cannot meet them, the project should not keep going on optimism alone. For Riverwatch node, that might mean the detector must reduce manual patrols, stay within power limits, and avoid so many false alarms that staff stop trusting it. An ethical limit can be just as firm. If the deployment captures out-of-scope information or creates unacceptable burden, that is a stop sign. Strong model metrics do not guarantee a good edge AI product. If the workflow does not improve, the system is hard to maintain, or the deployment creates unsafe or unsupported outcomes, the project still fails its real goal. Goals become practical when they are paired with checkpoints and decision rules. Milestones tell the team what to test along the way, and go/no-go criteria tell the team whether the results justify continuing. A useful project breaks the work into checkpoints like sensing, data quality, latency, workflow impact, and support planning. After each checkpoint, the team asks whether the evidence is strong enough to move forward. That structure helps fight sunk cost thinking. Instead of drifting forward because money and effort have already been spent, the team uses explicit rules to continue, pivot, or stop based on the real evidence. A quick criteria example makes the point clear. If Riverwatch node cannot get reliable seasonal flood data within budget, Stopping early protects the team from spending more on an assumption that no longer holds. Stakeholder alignment belongs in the metric itself. Success has to make sense to the people who fund the system, use it, maintain it, and live with its effects. That means the goal-setting conversation cannot stay inside the engineering team. The measures have to reflect the real trade-offs of the deployment, not just the preferences of one group. For Riverwatch Node, the detection target has to match response capacity, maintenance limits, and community expectations about what should be observed. If those views are not reconciled early, the project can optimize the wrong outcome and only discover it after deployment. Support is part of success, not a later add-on. A system that cannot be monitored, updated, or repaired is incomplete even if it performs well in the lab. Support goals should be written into the original plan. How often the system is checked, what counts as drift, who can retrain it, and what failures trigger rollback or shutdown. That planning keeps the system usable after the first deployment. That matters even more at the edge because the environment keeps moving. Sensors age, users adapt, sites shift, and the model could degrade quietly while everyone still assumes it is fine. The practical habit is straightforward. Define minimum viable performance, set milestones, and write the continuation rules before the investment gets heavy. That discipline does not slow the work down. It keeps the work pointed at a result worth shipping. Goal setting turns into a practical design tool once real constraints and real decisions enter the picture. The focus here is how goals shape what counts as success, when a project should change direction, and why that judgment matters in Edge AI. Good goals do more than fill out a project template. They give the team a basis for choosing metrics, comparing trade-offs, and deciding whether the work is actually worth continuing. The first design choice is deciding what progress means and what failure looks like. In Edge AI, that means translating a vague ambition into measurable outcomes and clear decision criteria before the work starts drifting. If that definition comes too late, the prototype starts setting its own standards. Teams then end up celebrating whatever the system does well instead of checking whether it solves the real problem under real constraints. A model can perform well and still fail the larger effort. The next question is whether the surrounding system actually works for the people and process that depend on it. A defect detector can look strong in test results and still fall apart on the plant floor. Timing, camera placement, false alarms, and maintenance all affect whether the model becomes useful in practice. What matters is the whole chain: hardware, data flow, human response, operational timing, approval, and upkeep. A benchmark would means little if the system loses on value, safety, usability, or trust. That broader view matters because deployment happens in a messy setting, not in a notebook. The right judgment includes fit with the task, the site, the people, and the organization itself. A useful goal set separates different kinds of success. Technical, systemic, and ethical needs each deserve their own minimum standard, because one layer can look fine while another is failing. That separation keeps the evaluation honest. It prevents a strong score in one area from hiding weakness in the others. Technical minimum performance asks whether the model is good enough to be useful at all. The usual questions are speed, reliability, resource use, and whether it survives the conditions it will face on device. Systemic minimum performance asks whether the whole arrangement works end to end. Staff need to respond in time, understand the alerts, maintain the device, and end up with a better process rather than extra burden. Ethical minimum performance asks whether the system stays within acceptable boundaries for people. It should not invite unfair treatment, unsafe automation, or outputs that sound more certain than they really are. Those layers often pull in different directions. A stronger model can make the workflow harder to trust, and a cheaper deployment can weaken coverage exactly where the system matters most. Ambition becomes manageable when it is broken into checkpoints. Milestones and go/no-go criteria stop the team from confusing activity with real progress. A milestone should say what evidence counts as sufficient. That makes continuation a decision based on criteria, not a guess based on momentum. An early checkpoint might require the system to run on the target hardware, find the defect class that matters, and respond quickly enough for an operator to act. Later checkpoints can demand stable behavior across shifts, lighting, and product variants. That kind of stage review is discipline, not pessimism. It protects resources by stopping overcommitment to a project that has not earned more investment. A project should not continue just because effort has already been spent. When the fit between goals and constraints is wrong, stopping or pivoting can be the responsible outcome. Sometimes the problem is not execution, but feasibility. If the available data, budget, or resources cannot support the target, the project is being asked to do something it cannot do well. That can happen when the rare cases are underrepresented, the hardware is too expensive, or the environment changes faster than a model can keep up. Adding polish does not fix a project whose core goals cannot be met. A disciplined abort decision saves time, budget, and credibility for work that can actually succeed. Strong teams treat stopping and pivoting as part of responsible decision-making, not as embarrassment. What counts as a good result depends on who is affected. Different stakeholders bring different measures of value, and those measures need to be part of the goals set from the start. Engineers may care about throughput, operations about maintainability, managers about return on investment, and affected people about fairness, burden, or visibility. If those voices are missing, the team can optimize the wrong thing with complete sincerity. A system can look tidy in isolation and still be unacceptable once human impact is included. Overcollection of data, unrealistic expectations, or extra burden on the people using it can make a technically correct design a poor one. Employers look for people who can define success, not just build models. The real judgment is whether a project should proceed, what risks it carries, and when the evidence says to stop. That means being able to name the metrics that matter and the limits that matter even more. It also means recognizing when a promising idea does not justify more time or money. That judgment shows maturity because it reaches beyond model training into product ownership. Choosing meaningful metrics, setting layered minimums, and treating ethics and systems as part of engineering are signs of responsible practice. Success needs to include performance, system impact, and values, because projects fail for more than one reason. When the stated goals cannot be met, stopping early can be the best result a project produces. Bootstrapping is the point where separate pieces stop being separate and start behaving like one system. The value is in learning what really happens when hardware, data, software, and workflow meet under real constraints. The first integrated prototype is rough by design, but it is complete enough to reveal the shape of the problem. That first whole system pass is what tells you whether the idea is viable and where the real risks live. Bootstrapping means the first time all four parts actually meet in one working setup. It is not about polish. It is about getting a real loop running so the project can expose its own limits. A good notebook result or a neat diagram can hide problems that only appear in context. Once the model sees live input, the device has to fit the job, and the workflow has to survive the mess of the floor. The system tells the truth. The goal is a small but connected pipeline that can answer real questions. Even a weak version is useful if it lets assumptions collide with reality, because unconnected parts only produce guesses. A production line is a good example because the system has to fit into an existing routine. The prototype should test whether Edge AI can help the inspection task without disturbing the work that already happens there. The first version should stay close to the current manual process. If workers already checked chocolate pieces by eye, the prototype can start by supporting that decision instead of trying to replace the whole station at once. A narrow first model is often the right move. One defect class, like a broken edge or a misshapen piece, is enough to establish a baseline and show whether the setup is useful before anyone tries to widen the problem. Early hardware should help the team move quickly and change easily. An off-the-shelf board or industrial PC often works better than a custom chip at this stage because the lesson comes from using the system, not from locking in the final device. The early prototype should leave room for change. That means collecting data and structuring the system so later hardware shifts do not force the project to start over. Good logging protects the project from early lock-in. If sensor placement, camera angle, or form factor may change, capturing extra context now keeps the dataset usable when the hardware evolves. The point is not to save every possible signal. The point is to preserve the options that matter, so later adjustments to lenses, lighting, or enclosure design still make sense in the recorded data. The same idea shows up in field systems like smart collars or environmental monitors. When the final sensor setup is uncertain, early multi-sensor logging can prevent an expensive restart after real-world testing begins. An integrated prototype reveals interactions that isolated tests miss. The angle of a sensor, the heat from a board, or the clarity of the interface can all decide whether the system actually works in practice. Separate components can each look fine on their own and still fail together. That mismatch is often where the real engineering work lives, because the parts change each other once the full system is running. Early integration lowers risk by showing what must be simplified, improved, or dropped. It also gives a realistic picture of time, complexity, and where redesign will almost certainly be needed. Real workflow testing turns assumptions into measurements. Once the prototype meets the field, the team can compare expected behavior with actual behavior and refine the dataset around what really happens. Technical success is not enough if the system makes work harder or less fair. The first review has to ask whether the prototype helps the people who will live with it every day. A useful prototype reduces burden instead of adding to it. If the tool speeds up inspection, that matters. If it creates friction, anxiety, or mistrust, that is part of the design problem too. The interface can look correct and still be a bad fit for the workplace. Too many alerts, too much attention demand, or a system that feels like surveillance can make the tool less valuable even when the algorithm performs well. Responsibility starts with the first prototype because design choices can amplify harm later. Visual or audio feedback has to reach the right people, and changes in workflow have to be judged for stress, confusion, and coordination cost. Bootstrapping needs a clear boundary because it is easy to confuse with later engineering work. The point here is discovery through integration, not refinement, scaling, or long-term support. This stage is not about squeezing out the last bit of accuracy or preparing a mature system for many sites. It is earlier than that, where the team is still learning what the real system should even be. The first working version answers one practical question: is this direction worth more investment? That answer can lead to growth, simplification, or a clean decision to stop in the current form. That possibility is valuable too. Finding out early that an idea should not grow saves far more effort than polishing a weak direction until it looks finished. After the first pass, the team should have more than a working demo. The important result is a clearer picture of performance, failure points, cost, and the assumptions that need revision. A useful prototype gives a baseline to beat. It shows how the system behaves in a real setting, what it changes for people, and which numbers matter when the next version is planned. A simple baseline can save time, or it can reveal that the current idea causes more distraction than value. Either result reduces uncertainty, which is exactly what the first prototype should do. That is the core idea to keep in mind. Build the smallest connected system that can reveal trade-offs and justify the next investment. Once that happens, the project has moved from guesswork to evidence. Bootstrapping turns an edge AI idea into a testable system. The point here is to see how data, model, hardware, and human workflow behave when they finally meet each other. A prototype becomes useful when those pieces are connected at once. That is when the real questions appear: whether the sensor matches the model, whether the model fits the workflow, and whether people can live with the result. The first target is not completeness. It is a small, realistic version that reveals whether the idea is worth refining and what kind of evidence still needs to be collected. A narrow first target keeps the prototype honest. If the scope is too broad, every failure is hard to interpret. If it is too tiny, every success can give a false sense of progress. Those choices should evolve together because each one constrains the others. A model trained on ideal images or a board that cannot keep up teaches very little about the system that will actually run on the line. The baseline sets the reference point. It should be simple enough to measure clearly, so later improvements can be judged against it instead of against vague expectations. A first baseline should solve one limited problem well enough to measure. In practice, that gives you a clean standard, such as one defect type in the chocolate line instead of a broad catch-all classifier. That outcome matters because it can save a project from unnecessary complexity. If a plain method meets the operational need, then extra hardware and maintenance may not be justified. Early hardware should let the team build, flash, log, and debug quickly. A capable development board often matters more at this stage than the most efficient final device, because slow iteration hides problems instead of revealing them. Data collection should keep future choices open. If the final sensor or form factor is still uncertain, the logging setup needs to capture enough context to compare alternatives later instead of forcing a single path too early. That approach protects the project from the first hardware guess. Multiple microphone types, for example, let you compare noise rejection, cost, and fit before the design becomes locked in. Physical details often decide whether the system works in practice. Mounting position, lighting, lens choice, enclosure material, and sensor response can all become the real constraints, so those assumptions need to stay visible. The first end-to-end build exposes interactions that separate parts never show. That is where technical performance, maintenance burden, and human impact start to appear together. A notebook result can break on live camera feeds, and a stable sensor can still be awkward to clean or maintain. Those mismatches only become visible when the whole system is running in context. Prototype review should include people, not only metrics. Alerts can overload workers, create surveillance pressure, or shift verification work unfairly. And early tests should also look for uneven behavior across shifts or groups. A system that improves speed but raises stress or hidden labor costs has not earned a large rollout. Those trade-offs have to be understood before scaling because they affect both the business case and the responsibility of the design. The real purpose of bootstrapping is better judgment. It gives enough evidence to decide whether to refine, redesign, or stop before the project gets expensive. By this stage, the team should know whether the baseline is worth improving, whether the hardware path is plausible, what data to collect next, and which human risks still need mitigation. Those answers shape readiness much more directly than any polished demo does. That judgment is the main skill here. It means turning an uncertain problem into a prototype, making disciplined trade-offs, and collecting enough evidence to avoid spending too much too soon on the wrong direction. Edge AI work runs as a feedback loop. Make a change, measure what happened, decide what it means, and revise again. That rhythm matters because the first idea always meets real constraints as soon as it reaches the field. A project here should feel alive rather than finished. Each adjustment is only useful if it produces evidence, and that evidence guides the next adjustment. The main challenge is coordination. Model work, data work, hardware work, and application work all affect one another, so progress depends on keeping them aligned. An Edge AI project is not just a model exercise. It moves through these four work streams together, and a change in one can force changes in the others. The application tells you what problem matters in the real world. The dataset tells you what the system can learn from, the algorithms determine how it learns, and the hardware sets the physical limits on memory, power, latency, and sensors. These are not a clean chain of steps. A hardware limit can narrow the model, a data decision can reshape the device, and the application itself can change once those limits become visible. Riverwatch node shows that the work can advance in parallel. While the dataset grows, the enclosure, alert logic, and field interface can still be refined if the team has enough evidence to make the next choice safely. The danger appears when each thread waits for the others. Once that happens, the project stops learning, so the team needs a way to keep moving through temporary uncertainty. The model may want more data, the sensors may not be settled, and the hardware may depend on model size. If everyone waits, the feedback loop breaks and nothing gets validated. A practical team uses a stand-in until the real dependency is ready. A development board or a simpler baseline model can preserve momentum and reveal the next constraint sooner. Algorithms are often the risky part because their final resource needs are hard to predict early. Extra memory, simpler interfaces, or a path for a larger model later gives the project room to adapt without restarting the design. The real device limits should shape the dataset, and the field requirements should shape the hardware and model plan. Good teams surface those limits early instead of pretending they do not exist. Speed matters only when it shortens the gap between a change and its consequence. Short cycles make it easier to learn what is working before too much time is spent on the wrong direction. The productive habit is small and disciplined. Adjust one variable, check the result against the goal, and then keep it, revise it, or drop it. That approach avoids the trap of training on everything at once before you know what matters. A smaller slice of data is often the safest way to learn quickly. If it preserves the important variation, it can expose regressions early and save weeks of work on a flawed path. Limited tests make trade-offs visible. A change that helps one narrow case, but hurts the field cases that matter, is much easier to catch when the iteration is still cheap. A missing component should not freeze the team. The right question is what can be validated now, with honesty about the limits of that partial result. As evidence builds, goals can shift. That is part of the process, because the point is to fit the system to reality, not to defend the first draft forever. Iteration includes revising the target itself when new evidence says the original plan was off. That is not disorder. It is the mechanism that keeps the work grounded. A model can improve while the system still becomes harder to use or harder to govern. Field impact, worker safety, and organizational fit all belong in the review, not just the metrics table. Sometimes the first goal was too narrow, or the operating context makes a different design better. The right response is to update the plan with stakeholder approval and treat that shift as part of the learning loop. When the target changes, the decision needs to be recorded, not hidden. That keeps minimum viable performance and go/no-go thresholds meaningful because they stay tied to the real operating conditions. Ethical questions cannot wait until the end. Every new result can change who benefits, who carries risk, and what the next data or design choice should be. Uneven performance across groups should trigger a fresh look at the data source, the deployment setting, and the purpose of the system. A metric problem can become a fairness problem very quickly. A site that works well and another that does not may call for better examples, a different alert rule, or even different hardware. Ethical review keeps those options visible before the pattern hardens into harm. Each cycle should leave a record of the model version, dataset slice, hardware revision, rationale, and decision. That history is what makes later support, deployment, and audit work safe. The practical value shows up in real teams and real hiring decisions. People are expected to move across data, hardware, and product constraints while staying traceable, fast, and accountable. Employers look for speed that still leaves a clear record of what changed and why. On-edge systems, communication, and ethical judgment are part of the technical job, not extras on the side. The lasting model is a connected feedback system. Make small measured changes, substitute intelligently when blocked, revise scope honestly when evidence demands it, and document enough for the next phase to be safe. Iteration in Edge AI is about proving what changed and what that change means. The point is to use visible evidence from the system, the data, the model, and the device to decide whether to keep going, adjust, or stop. A good iteration leaves a trace you can act on. That trace might be a metric, a log, a field observation, or a hardware limit, and it tells the team whether the change helped or created a new problem. The loop works only when the full stack is part of the conversation. Application behavior, data quality, model choice, and device constraints all affect one another, so a change in one layer can shift the others. A pre-processing change can make the system look better in a test set, while making it less useful in practice. A smaller model may fit the device, but still miss the cases that matter on the ground. Fast feedback is a risk control tool. When the hardware team, data team, and application owners see problems early, the team can correct mismatches before they harden into expensive mistakes. The safest early test is small, but it still has to resemble the real setting in the ways that matter. If the sample is tiny but distorted, the team can build confidence for the wrong reasons. That means keeping the same sensor type, the same noise or lighting pattern, the same class balance, or the same latency pressure. The goal is not realism for its own sake. It is learning from a slice that carries the same constraints as deployment. A Riverwatch node prototype can learn a lot from one pre-processing change on a small data slice and a limited device setup. The useful questions are practical. Do alerts arrive sooner? Does noise rise? Does the device run hotter? And does the battery drain faster? Metrics matter, but visual and operational evidence often reveal what the numbers hide. A score can move in the right direction while the real behavior still misses the needs of the application. A confusion matrix, an overlay on a camera frame, a live dashboard, or a device log can expose patterns that a single summary score hides. That mix shows both whether the system changed and whether the change matters in practice. A model may score well on validation data and still point to the wrong region on a real inspection line. When the visual output disagrees with operator expectations, the issue is readiness, not just model quality. Minimum viable performance is about decision-making, not applause. If the system is not ready, the right move may be to narrow the scope, change the target, or stop forcing the original plan. Dependencies can freeze progress when one piece cannot move until another exists. The way through is to keep learning with substitutes instead of waiting for the perfect setup. The model may need a device profile, the device may need a smaller model, and the dataset may need field data that has not arrived yet. When that happens, a simulator or bench test can keep the iteration alive. A smart collar project can still make progress with a simulated signal stream or a partial rollout on a few units. Those substitutes produce useful evidence about alerts and behavior without waiting for the whole production system. Temporary evidence reduces deadlock, but it must never be mistaken for full operational evidence. Clear labeling keeps the team from confusing a rehearsal with deployment reality. Every loop needs a decision, and that decision should rest on agreed criteria. Technical performance matters, but business readiness and ethical readiness matter too. A system can look strong on a metric and still fail a worker impact check, demand too much manual intervention, or produce uneven outcomes across user groups. When the goal itself is unrealistic, the responsible response is to narrow the scope or reset expectations. That difference is what strong engineers learn to judge. Employers value people who shorten iteration cycles without losing rigor and who can turn test results into decisions that product and operations can use. Each pass through the loop should leave a record behind. That record becomes evidence for the next step and a guide for support after the system moves into the field. Good documentation captures the change, the evidence, the inference, and the decision that followed. That makes deployment safer and prevents the team from relearning the same lesson later. For Riverwatch, a smaller pre-processing window may reduce delay while increasing noise sensitivity. For inspection, a model may match the lab benchmark but still miss operator expectations, which points to labels, thresholds, or the interface rather than another retrain. Progress in edge AI comes from disciplined change and disciplined judgment. That habit connects application behavior, data quality, algorithm choice, and hardware limits without losing control of the system. Deployment starts the moment a model or system meets real constraints, because that is when hidden problems begin to matter. The goal here is to understand deployment as part of the life cycle, not as a final victory lap. A prototype can look fine in isolation, but real use changes the stakes. Once hardware, data, and users are involved, the work has consequences that development alone cannot reveal. That change in mindset affects risk management. Early, controlled exposure lets you learn where the system fails before you depend on it, instead of discovering those failures after the rollout is already large. Deployment sits inside the larger life cycle of build, test, release, and support. The important idea is that the system keeps evolving even after it leaves the lab. In practice, those boundaries are fuzzy. Hardware still gets tuned, models still get adjusted, labels still get corrected, and real-world feedback keeps shaping the next version. Edge AI uses the word in two ways. One is installing the inference stack on target hardware. The other is placing sensors or machines into real environments so they can collect data and act on it. A laptop success does not guarantee device success. Memory, latency, power, heat, sensors, and connectivity can all change the outcome once the system is in the real setting. Once the system is running in the field, it starts producing evidence about its own behavior. That evidence tells you what it sees, what it predicts, and how people actually use the results. The safest first step is the smallest real exposure that still teaches something useful. That usually means one device, one site, or one small group rather than a full rollout. A staged rollout keeps the risk contained while the team learns. Each limited step gives evidence about performance, failure modes, and whether the system is ready for wider use. With the livestock collar example, deployment begins when the system meets real animals and real field conditions. Synthetic data cannot expose the motion, drift, and messiness that appear outside the lab. Recording synchronized video gives the team a ground truth reference. That lets them compare the collar's outputs with actual behavior and see whether the hardware and labels hold up in practice. Expansion should follow evidence, not enthusiasm. If the first trial reveals short battery life, data dropouts, or uneven accuracy, those findings guide the next revision before any broader release happens. The path usually moves from prototype testing to a controlled field trial, and only later to wider rollout. Each stage adds more reality, so each stage needs its own checks and learning goals. After the first working version is out in the world, the main question changes. The focus shifts from proving the idea to keeping it reliable, useful, and safe over time. That is the handoff point from development to support. The system no longer needs constant invention as much as steady operation under real conditions. A system at this stage still needs care. Monitoring, hardware swaps, recalibration, and retraining all help preserve usefulness when the environment or the data changes. That skill matters because edge AI success depends on more than model accuracy. Teams need engineers who can balance integration work with real operational constraints and avoid preventable failures. A limited deployment lets hardware, software, users, and environment prove they can work together. It is a controlled test of coexistence before the system is trusted at scale. The workflow is connected, not separate. Real data and real constraints should enter the loop early, because that is how surprises are reduced later. A simple rule helps place any project on a map. Once real hardware or real field conditions are involved, deployment has already begun. If refinement is still happening there, development and deployment are overlapping. After the performance threshold is met, support becomes the main job of keeping the system healthy. That framing captures the edge AI mindset well. Building does not stop at release. Release is the point where the system begins its real life under constraints that have to be managed carefully. Deployment is the point where edge AI becomes observable in the real world. The focus here is on what counts as evidence, how field use exposes the truth, and why rollout has to be treated as part of validation, not just distribution. Once the system is running in place, the discussion changes from theory to evidence. Hardware limits, workflow pressure, and environmental conditions all become part of the result. And that is what makes deployment such an important test of whether the development loop is working. The key shift happens when the prototype leaves the lab and meets the conditions it was built for. That moment tells us whether the system can survive contact with actual use, not just control testing. Sometimes the change is software moving on a target hardware. Other times, it is the device itself being placed in the field. Either way, the system now has to deal with power limits, movement, weather, and people using it in ordinary ways. Those two cases point to the same practical reality. The system has crossed from controlled conditions into a setting where it has to justify its existence by working reliably. A limited rollout is useful because it reveals problems while they are still manageable. It also catches mismatches between software and hardware, like poor camera placement, weak battery life, or a workflow that is harder to support than expected. Field results become much stronger when they can be checked against something concrete. Visual records, labels, and direct observation give the team a way to compare what the system reported with what actually happened. That comparison gives the team a reference point for evaluation. It shows where the system agreed with reality, where it drifted, and where the mismatch first appeared. A device can still be working while seeing the wrong thing, and a detector can still score well while missing behavior that matters in the field. Changes in lighting, grouping, posture, or position often expose weaknesses that never showed up in the lab. Those phases work together as a loop rather than as separate boxes. Real use produces evidence. Evidence updates the system, and the updated system goes back into the field with better support behind it. A livestock rollout shows how this works in practice. The team starts small, checks the data against field evidence, and expands only when the system proves it can handle real conditions. The first rollout puts the system in contact with reality without exposing the whole herd to risk. That gives the team representative data that a lab setup could never fully reproduce. At that stage, the important question is alignment. The team wants to know whether the collar events match what the video shows and whether the misses cluster around particular behaviors or conditions. Gradual expansion is a way to manage risk while still learning. Each stage asks a different question about sensing, labeling, and scale, so the team can catch the next problem before it becomes a costly one. A small project like Riverwatch Node follows the same pattern. A few devices are enough to show whether installation is practical and whether the system behaves the way the team expected in the field. A good rollout begins with clear decisions about scope, measurement, and growth. Without that structure, the team may collect a lot of activity but very little useful evidence. Those four questions keep deployment grounded. They define the first users, the setting, the evidence to watch, and the conditions that must be met before the system grows. That question limits the first audience on purpose. A narrow starting group makes it easier to observe behavior carefully and reduce avoidable risk. Location matters because the environment shapes performance. A model can behave very differently depending on the space, the motion, the connectivity, and the physical setup around it. Good deployment metrics are not only technical scores. They also include operational signals and human outcomes, because a system that is accurate but awkward may still fail in practice. Scale up should wait for clear criteria. That makes expansion a decision based on evidence, not enthusiasm, and it keeps the next rollout stage honest. High benchmark scores do not matter if the system creates extra burden or misses the behavior it was meant to support. A rollout is ready only when it clears the operational threshold that the real users actually feel. Those checklists help turn the deployment plan into something concrete. They keep the pilot scope, observation points, and support monitoring tied to the same evidence trail the team is using to judge readiness. That same discipline matters in the job market. It shows that you can manage risk, validate in real conditions, and keep a rollout moving without treating every issue like a crisis. Deployment and support are different responsibilities, but they start to overlap as soon as the system is in use. The earliest field data often becomes the material that support teams need to keep the system healthy later on. Support begins when a main job shifts from getting the system installed to keeping it effective over time. Drift, workarounds, failure clusters, and maintenance costs often show up during those first deployments, so the handoff is never completely clean. The practical sequence is a continuation, not a cutoff. Each pass through the field teaches the team something, and that knowledge feeds the next improvement cycle. That is why deployment matters so much in Edge AI. Treat it as an early, evidence-driven stage, and the system becomes safer to roll out, easier to refine, and better aligned with the hardware and the people using it. Support begins after deployment, but it is part of the system's real life, not an afterthought. The point here is to understand why keeping an Edge AI system healthy matters just as much as getting it running. Once the system is live, the work changes from building to sustaining. A model that reaches production still has to prove it can keep doing its job in messy, changing conditions. Edge AI does not stay inside a controlled lab. Weather, users, devices, and workflows all shift over time, so the system's behavior can shift too, even if the code never changes. Good support starts before deployment because you need a plan for monitoring, response, and updates from the beginning. People who can think that far ahead are the ones employers trust to keep a system credible after launch. Performance drift is the normal reason support exists, so the next step is to understand where it comes from. Once that idea is clear, the need for monitoring becomes much easier to justify. A deployed system keeps meeting new conditions. Light changes, sensors age, and users adapt their behavior, so the data the model sees slowly moves away from the data it was trained on. The danger is gradual decline rather than sudden failure. A few extra misses or more false alerts can slip in quietly, and support exists to catch that erosion before operators lose trust. The Riverwatch node makes the idea concrete. Seasonal water changes, residue on the casing, and shifting wildlife patterns all push the system into a new operating condition. So the team has to manage change instead of assuming launch solved everything. Monitoring only matters when it feeds evaluation. The two belong together because you need measurements not just to collect data, but to decide whether the system is drifting and what that drift means. A metric is useful when it helps you judge the system's state. That is how you turn raw numbers into evidence about the model, the data, or the environment. A weak confidence score, missed detections, or too many alerts can point in different directions. Support teams have to separate sensor problems from model problems from real environmental change because the fix depends on the cause. Evaluation does not end at rollout. It keeps linking evidence to action, so the team can decide whether to leave the system alone, make a small adjustment, or redesign part of it. Maintenance is the work that keeps usefulness from fading. Some of it changes the model or software, and some of it changes the surrounding workflow so the system still fits the job. Technical maintenance includes updates, patches, recalibration, and retraining. Operational maintenance changes how people use the system, how alerts are routed, or how hardware is checked in the field. Not every change deserves a response. The real question is whether a measured change affects reliability, safety, fairness, or cost enough to justify action. With Riverwatch, the response could be recalibration, retraining, or a workflow change depending on what the evidence shows. Support turns field observations into a specific plan instead of a vague feeling that something has gone wrong. Deployment, evaluation, and support are different questions, but they do not live in separate boxes. The practical overlap between them is what makes the life cycle usable in the field. Deployment asks whether the system can enter the field safely. Evaluation asks how well it performs. Support asks how to keep it useful as conditions keep changing. Early deployment often reveals what support will need later, and evaluation may continue while the system is already in use. That overlap is a strength because it lets the team prepare before problems become expensive. The healthiest habit is to treat support as the same job under new conditions, not as cleanup after the important part is finished. Teams that plan for support early usually stay calmer when the environment starts to change. That is the larger life cycle idea. Shipping is not the end because a deployed system still has to survive in the world. Support makes that survival possible, and it sets up the next stage of development. Support is the phase where an edge AI system proves it can stay useful after release. The focus here is on what changes after deployment and why ongoing care becomes part of the design from the start. A project is not finished when the model first works in the lab. Once it enters a field, factory, vehicle, clinic, or outdoor site, it meets conditions that were never fully controlled, so the team has to keep watching and adapting it. A model can be sound at launch and still become less reliable later because the inputs shift, sensors age, users behave differently, or the environment changes with the season. That kind of loss is usually gradual, which is why support is about catching mismatch before it becomes obvious failure. Support belongs in the life cycle because the question has changed from can it be built to can it remain useful? The work now is to care for a service in operation, not just to ship a model once. That stewardship usually has three parts: watching the system, keeping the surrounding setup healthy, and making changes only when evidence supports them. The point is deliberate adjustment, not constant tinkering. Monitoring tells you whether something important is shifting. Maintenance keeps hardware, software, and routines working well, and updates range from small recalibration to full retraining when the evidence says the system needs it. Accuracy alone does not tell the whole story once a system is deployed. Support has to look at the inputs, the operating conditions, and the effect on the job, because a single metric can hide real change. A deployed system may look fine on paper while the sensor stream, the environment, or the user experience is drifting away from what the model was trained for. That is why support needs a wider view than the headline score. A river node can miss more events after the signal shifts. A smart collar can become less useful as movement patterns change, and an inspection system can stay confident while lighting or workflow alters the image stream. In all of those cases, the score matters less than the conditions producing it. That is why evaluation metrics stay useful after launch. They stop being just a readiness check and start acting like an early warning system for drift, aging, or misalignment with a real task. Drift is part of normal deployment life. Edge systems live in changing environments, so the support question is not whether drift will happen, but how quickly it can be recognized and handled. Weather changes, worn sensors, altered lighting, new usage habits, and shifting workloads all move the system away from the conditions it first saw. In many deployments, that is the background setting, not an unusual event. When misses rise, the team has to trace the cause, not just the symptom. The answer may point to a software fix, a recalibration, a retraining cycle, or an operational change such as mounting, sampling, or threshold adjustment. Sometimes the fix is tiny, like a sensor recalibration. Sometimes it is a patch for data handling or pre-processing, and sometimes the model is fine while the deployment process itself needs to change. A support problem does not have to look like a crash. A system can keep running and still stop being a good fit for the environment or the workflow it serves. A deployment may still classify, detect, or flag events. Yet its value can shrink if the environment has changed too much or the operating cost has grown too high. The model is active, but the service is losing usefulness. That is where minimum viable performance and quit criteria matter. If the system can no longer meet the technical, operational, or ethical standard it was built to satisfy, the responsible choice may be to pause, revise, or retire it. Support is where the technical signals and the real use signals meet. A metric drop may explain user complaints, or a user complaint may expose a problem that the metric alone would never reveal. This is the difference between a demo and a production system people can trust. Support shows that the system can keep working, and that reliability is part of the actual product. A demo can show that a model performs once under favorable conditions. A supported deployment has to hold up over time, which is what separates a prototype from something dependable. That is why the job does not end at training. Teams need people who can instrument monitoring, detect drift, interpret metrics, schedule updates, and decide whether a deployment still belongs in the field. Support is the long-tail phase that keeps an edge AI deployment useful after the first version ships. Treating the system as something living and responding as conditions change is what preserves value over time.